Once we've trained a decision tree model, how do we go about using it to make predictions? Well, the way you make a prediction on an observation is you start at the very top of the tree, the root node. At this point here, you're going to answer this question. In this case, is the petal length less than or equal to 2.45? If the answer is true, you move to the left. If it's false, you move to the right. Now, depending on where you are, what node that observation now resides in, you repeat the process until you've reached a terminal node, until you've reached a leaf. So let's say you go about answering these yes or no questions for an observation. You want to make a prediction. And let's say you reside on this terminal leaf at the very end, right here. If we look at this, there were 48 training observations that make up this terminal node. Out of those 48, 47 reside in class 1, and only one observation resides in class 2. Since the dominant class that makes up this node, this terminal node, is class 1, every observation that resides in this terminal node you will predict in class 1. If our observation resided in this leaf here, if we notice in this leaf here, all the training examples that resided in this leaf were all in class 0. So any observation that resides in this leaf are going to be classified as class 0. And if we look at this example here, 43 samples of class 2. If we reside here, we predict class 2. And notice these leaves here, yes, there is a dominant class, but not by much, not going to dominate by too much. So if an observation resides here, only six training observations, 4 of those are in class 2. We're going to predict class 2. But we understand if the observation resides in this terminal node here, since one class isn't as dominant, then perhaps the prediction won't be correct. There's more uncertainty in our prediction here. Let's go back to the question of what metric is this model using to create the splits? We understand that we're creating splits in our space. The model has to decide at a node what is the best question to ask to perform the split. And let's define what does best mean. So there's 2 different metrics we can use when we are dealing with classification decision trees. One metric is the Gini impurity metric, which is a measure of node impurity. It's going to be equal to the probability of misclassifying an observation if we were to randomly label based on the distribution of labels of the nodes. In other words, let's say you have a node, and in that node you have 3 classes, class 0, 1, and 2. And let's say there's an equal chance to be in class 0, 1, and 2. That means for a random observation, you're going to randomly choose one of those classes to predict it on. And then Gini impurity will be a measure of the probability of misclassification. The equation for the Gini metric is defined here. Notice P of M, K. K represents a class, a certain class. So if we have 3 classes, we're going to add 3 different values. And P represents the fraction of observations in class K that reside in node M. So M here is going to be the indice to refer to a particular node. So the Gini impurity metric value for a certain node M is equal to this equation. So we have to calculate the fraction of the observations of each of the classes. If we have a situation which we only have 2 classes, 5 observations in one, 5 observations in the other, then the Gini impurity metric will have a value of 0.5. Since this Gini metric is a measure of impurity, what do you think its value would be if all the observations in this one node are all the same class? In other words, let's say we have 10 observations in a particular node and they're all class 0. what should it be? Its Gini impurity metric. Since it's a measure of node impurity, at this situation, this node is pure. This leaf is pure. All the observations that define this node are all the same class. There's nothing to pollute it, so it's a pure node. Because of that, the Gini impurity metric will have a value of 0. So if we run the math using the Gini impurity metric, we would see that it has a value of 0. Let's plot the Gini metric. So here is a Gini metric just for two classes, class 0 and class 1, and we notice that it has a peak value of 0.5, which occurs when the relative mix is equal. It's 50-50. So as our node becomes more pure towards one class, it reaches 0. If it becomes more pure on the other end, the other class, it's also going to reach a value of 0. Now the Gini metric is one possible metric we can use for our problem. On the other hand, we can use a different metric called entropy. You might be familiar with entropy in the realm of chemistry, which is a measure of disorder or the number of microstates a system can be. This idea of entropy has proven useful in other fields, so other fields have taken the concept of entropy and defined it for their respective field. So in the field of information theory, we can view entropy as a measured amount of missing information for a process. And the more information that we are missing for a process, the more uncertainty exists in the process we're analyzing. Okay, so the equation for entropy is defined here. So once again, P of M of K is going to represent this relative fraction. It's going to represent the fraction number of observations that are in class K in node M. Let's go ahead and calculate the entropy for those two cases we observed. A case in which we have two classes, and there's 5 observations in class 0, 5 observations in class 1. Let's see what its value for entropy will be. If we look at here, this is the worst case situation. We have an equal mix of both classes. So what ends up happening is we have a very large amount of entropy, in this case a value of 1. On the other hand, if we have a node in which all the observations belong in one class, then its entropy will be very low. In fact, it will be 0. So there is no entropy here, there is no disorder, there is no missing information. You could think of a node that all your observations belong in the same class. There is no uncertainty there. They all belong to the same class. It's like saying if I had a coin in which when I flip it will always either turn up heads or tails. In this example here, if I have this coin that would, let's say, always turn up heads, there is no uncertainty in the process. Every time I flip the coin, it's always going to turn up heads. It's a pure coin in some regards in that way. So it has no entropy. There is no missing information in this process. There is no uncertainty here. Now the difference between Gini impurity and entropy are pretty much, there isn't much differences between these two metrics. In fact, we can go ahead and modify them. We can choose them. We can view them as a hyperparameter to our model. And using one or the other isn't going to create too much differences in the performance of our classifier. So yes, it is a hyperparameter that we can play around with, but it's not going to be a dominant hyperparameter for our model. There are other hyperparameters that are more dominant that perhaps we should spend more time talking about how we go about choosing a good value for those values of those hyperparameters are more dominant in the process. But just keep in mind you can go ahead and switch one or the other. By default, scikit-learn is going to use entropy, but you can set it equal to Gini and it would use the Gini instead.